Hey guys, what's up? My name is Gabe, and this is Games with Gabe, and this is the next episode in the Coding a 2D Physics Engine in Java series. In this episode, we are going to continue going through Box2D Lite's source code. Now let me just reiterate, the reason we're doing that is because we're trying to reverse engineer his solution for this problem, which is, if we have two boxes colliding like this, how do we determine what the contact points are? And you can see that this is the contact point we are looking for in this scenario, and the normal, which is this arrow right here. So that is the reason we are going through this source code, and specifically for two boxes, because that is the next step in our physics engine. So let's continue going through his source code. And we stopped right after we performed the separating axis theorem in a very condensed manner, which was all this code right here. And once again, let me just reiterate, we realized that from our situation, which we have right here, that the axis of separation is the x-axis. So it's basically this normal, and this is the penetration depth, which was minus 0.1, okay? And we have all that information sort of here too. You can see that it says minus 0.1, and then we would end up using the box A's face x. Okay, so that's sort of the long-winded way of saying it. So if we look at the code, what would have ended up happening is we would have remained with this axis as face A's x, separation would be negative 0.1 or face A's dot x, and then the normal would be positive rotation A dot column 1 because it's pointing in the right direction. And then all these if statements would basically be skipped because this is the best axis of separation, or best axis of penetration, I guess I should say. So if we scroll down, let's actually just write down all that information because we're about to step into another pretty big portion of code. So I'm going to go ahead and go over to here, and then I am just going to write down step 4, and we're just going to write down all that information that we got, which was separation equals minus 0.1. The normal is 0.1, and we are going with face A's axis. X-axis, I should say. Okay, so these are the details we're going to save, and then I am just going to move all of this information out of the way because we don't really need it anymore, and it is just kind of cluttering up our space. All right, so with all of that cleared out of the way, let's take a look at the variables we are going to be requiring. So we see here that I've written down too that he says we're going to be setting up the clipping plane data based on the separating axis. So basically the front normal will be the normal in the direction of the collision. So if we look at this visually, this is the front normal. The side normal is perpendicular to the front normal. So the side normal would be pointing to the right in this particular scenario. The incident edges are the two edges that the collision happened. So we have right here the incident edge, which is this edge, and then the reference edge, which is this edge. Okay, so we know visually what we're dealing with here. Now let's actually calculate the values that we will get. And we're going to fall into this case face AX, right? Because that is the axis that we have. So let's just start writing down. So he says front normal equals normal. So let's write that down. I'm saying front normal equals the normal, which is just 0, 1. So we'll just rewrite 0, 1 there. Then we can see that he says front equals position A dot front normal plus HA dot X, okay? So we're going to look at this visually, see what this is, and we are also going to calculate. Let's calculate it first real quick. So he says front is equal to pose A. So if we look at pose A, that's 2, 2, dot front normal. So if we look at front normal, that's just 0, 1, plus HA dot X, which is, if we look at HA, that's just 2, which equals, so if we do 2 times 0, that's 0, plus 2 times 1 is 2, plus 2 is 4. Okay, so what is this? This is pose A dot front normal. What is that doing? That's projecting position A onto the front normal. Okay, what does the front normal look like? The front normal is an arrow that looks like this, right? It's just pointing to the right. So if we draw a line down here and just pretend that's straight, what front normal, or what front is we're projecting the position onto the front normal. So basically we're saying, okay, well, if we project this, then that will end up down here. Which is just basically, if this was 0, then this would be 2, okay? Plus, we're adding in the half width, so then we end up right here, which is just 4, right? And that's what we have here. And if you look at that, that actually makes a lot of sense too, because he's saying the front is basically just this position right here, which it is. If we're looking at this in terms of our collision, this is the front of the collision right here from A's point of view. Okay, so that is what that first variable is. Then if we look at the code, he says the side normal equals rotation a dot column 2. So remember how we talked about the rotation columns basically contain the normals that we'll be needing. And if we look at rotation a column 2, which is this, in our case it's row 2 because I've flipped the way that he uses them, then basically what we see is that this is 0, 1, which is just pointing up. Okay, so that makes sense too, because if the front is to the right, then the side would be to up, okay? So we'll say that the side normal equals 0, 1, and this is wrong. Front normal should be 1, 0, not 0, 1, which wouldn't change the value over here in that case because it's the same. So we're good on that case. But let's continue through. So then the next thing we have is the side. So he says the side is equal to position A dot the side normal. And so what's happening here is very similar to what just happened with the front. So let's calculate it first, and then we'll see where it relates. So side equals position A, which is just 2, 2, dot the side normal, which in this case is 0, 1. And this is actually 1, 0. We just messed that up. No plus 2 this time. So if we do this, this is 2 times 0, 0. 2 times 1 is 2. So that's equal to 2. What's happening here? So I've just drawn a vertical line here. What's happening is we're just projecting the position onto the side, okay? So if this is 0 in this case, then if we project the side, then what we end up with is this point right here. We're saying that's the side, okay? And you'll see why he calls that the side too in just a minute with the next two variables. So if we look at the next two variables, he says the negative side equals negative side plus half of a, the y, and then positive side equals positive side plus ha dot y, okay? So if we calculate that, he's saying negative side equals negative this side, so negative 2, plus half of a's y. So if we look at ha dot y, that's 2, which is 0. Positive side, he's saying, is equal to positive, the variable side, so in this case 2, plus, and then ha dot y again 2, which equals 4. What's he doing? Well, what would this be? So this would be this going down half of a's y, width, so that would be the negative side. And then if we were to do this one, this would be the positive side, okay? And I hope you can see this is just the top and the bottom of the square. Now, the reason he's doing these as dot products is because if the square was rotated, then it would actually be more like this, and then we'd be projecting onto some axis like this. This would be negative side, this would be positive side, okay? So projections keep it so that we're nice and neat and we're not using weird radians and weird numbers, irrational numbers and everything. This is so much easier to deal with things this way. Okay, and then he says negative edge equals edge 3, positive edge equals edge 1. Let's just take a look at that, make sure that all lines up. So if we look at our diagram over here, edge 3 is the bottom of edge. Well, that lines up. Negative edge is the bottom edge. And then he says positive edge is edge 1. Well, positive edge is edge 1 if we look at the positive side. Okay, so that all lines up correctly too. And then we jump into this function, which is a little bit tricky when you're first looking at it. It certainly was for me. So compute incident edge. Incident edge is what he passes in. And if we look at that, it's a clip vertex, an array with 2 clip vertices. And then he passes in HB, so the half size of B, position of B, the rotation of B, in the front normal. So let's take a look in depth at what this does. But before we do, let's take a look at what incident edge actually is. So clip vertex, if we look at his source code, a feature pair, which looks like this, and then it also consists of a vertex. And I'll actually drag that into our drawing so we can see that right there along with everything else. All right, so I've just written down the clip vertex down here. So it's a vector 2, V, and a feature pair, FP, which consists of in edge out 1, out edge 1, in edge 2, out edge 2. We will see how all of these sort of formulate the solution in just a second, but it's good to have that structure there so we know what's going on. Then if we go back to the code, we just want to sort of write down this function so that we know what's being passed into there, and then I'm going to click into the function and we'll start going through this source code line by line. All right, so you can see I just wrote down compute incident edge, which is, I just basically copied the function so that we know what the variables are. Okay, so back in the code, he says first, the normal is from the reference box. Convert it to the incident box's frame and flip sign. And so I wrote here, in other words, rotate the normal to the other box's local space. So that's what he's doing right here. First, he's saying, let's rotate front normal, which is what was passed in, to the box we're working on's local space, which he does negative rotation t times normal. So in our case, what would happen is that would just basically mean that n equals negative front normal, so just negative 1, 0, because if we're rotating this into box's local space, well, it is in local space, right? Because these boxes are at 0 degrees. But if this was some other thing, like if the box was rotated, then it would basically just have the normal looking this way, or actually this way. Because what we're doing is we're saying, hey, rotate this normal, which is pointing this way, into his local space. So to him, the collision is happening this way, which is why we flip the sign. Okay, and so he basically does that, and then he also gets the absolute value of n. Then we want to figure out which edges correspond with the vertices that could possibly be penetrating the box. So each incident edge has 2 edges, which leads to one possible vertex being inside the other box. So put simply, what he does is he first finds out where is the normal bigger? Is it the x or the y part? So is it pointing more up or is it pointing more right and left? Then he says, okay, now let's figure out, is it pointing to the right or is it pointing to the left? In our case, it is pointing to the left. So we would end up falling into this else block. And basically all these other blocks are just what to do, how to set it up appropriately if the vertex or the normal is pointing in a different direction, okay? So basically, let's go through this else block because that is where we lie. So he says c0.v.set negative h.x, h.y. Okay, so let's go back to our code, or let's go back to our drawing. So he says c0, and I'm just going to write c0 like this, and he says set the vertex, so v, to negative h.x, h.y. Well, what was h? H was hb, so negative 1, 1 is what he's saying to set it to. Then he says set the in edge to edge 1 and set the out edge to edge 2. Okay, so what he's saying is this is the in edge, it's coming in through here and it's going out through here, or at least that's what we're guessing. And specifically that's happening on this box, right? So this is the in edge of C0 and this is the out edge of C0, okay? And if we look at negative 1, 1, what does this represent in terms of the box? Well, that represents the box's top left corner. This is, if we look at this, right, if we go negative 1, then positive 1, we end up at the box's top left corner. So already we're getting close to those contact points. Now, if we look at the next portion of the code, it does the same thing for C1, except it just sets edge, in edge to edge 2 and out edge to edge 3. So if we look at that, basically what we do is we say C1 equals negative h.x, negative h.y, so negative 1, negative 1, and then edge 2, edge 3. And so if we look at this, edge 2 is this way. So he's saying the in edge for this one is right here, and the out edge is right here. And that points to this vertex. Okay, cool. So if we look at that, that's negative 1, which is this vertex, right? So basically what we're doing is we're just sort of finding the edges that correspond with the vertices that could potentially be in this, could be penetrating the other box, which we find out it figures out exactly correct. So we do all that, and then the last step is we rotate the result back out of local box space back into world space. So you'll notice he says pose plus rotation times c0.v and pose plus rotation times c1.v. So first he rotates it back into world space, then he adds the position, which translates it to the actual spot. So if we look at our drawing, then that would basically be like, okay, so C0 plus equals, it's B's position, which is just 4.92, which would end up giving us 3.93. And if we look at that, that's actually what this corner is in world space. So we're just getting this vertex in world space, and then we could do the same thing for C1. And so if we add 4.92 to that, then we end up getting 3.91. Okay, which is this vertex in world space. Cool, so nothing too fancy going on there. We basically just got the vertices in world space, and then we also got the edges that are sort of the incident and reference edges, the possible incident and reference edges, okay? So that is this function. It's actually not that difficult. It took me a long time to understand what was actually going on there though. Okay, so that's what we did. We just computed the incident edge and we placed it inside of this incident edge, okay? So now if we scroll down, past this switch statement, Then we see clip the other face with 5 box planes. So this is where we're actually going to start clipping the points, okay? And so he says first we're going to clip it to box side 1. And so what he does is he passes in clip points, incident edge, negative side normal, negative side, negative edge. And we'll take a look at what's happening here visually, and then we'll also follow through this code. So I'm going to jump into this function. I'm also going to copy that function definition into our drawing so we know what's going on. Okay, so in the drawing, you can see that I just sort of consolidated some of our variables. I just moved up the final vertex positions, 3.93 and 3.91. And then I just wrote down this clip segment to line with all the variables that were being passed into that function, okay? So that we can sort of follow along. So now, if we go back to the code, then we notice that the first line says start out with no output points. So we're starting off saying, hey, we have no output points. We have not clipped anything yet. Then it says calculate the distance of endpoints to the line, okay? So then it says distance 0, and I'm just going to call that D0, equals dot, so normal dot v and 0 dot v minus offset. And if we look at offset and we look at what we passed in, that offset is just negative side edge, just this negative side variable, okay? Which if we look up here is just 0. So one more time. We do normal dot v and 0 dot v minus offset, that's just 0. So if we go ahead and actually calculate that, we can say d0 equals, and so it's just the normal, which the normal we passed in is negative side normal, so that would just be 0, negative 1, okay? Dot, and then we are dotting it with v and 0 dot v, so this vertex right here, which is just 3.93, minus offset, which is 0, so then this would end up being 0 times 3.9 is 0, plus negative 1 times 3 is negative 3. So just negative 3. D1 is very similar, except we just dot it with the vertex here for C1, which is 3.91 minus 0, which you can probably guess is just negative 1. Okay? So what do these values represent, though? Basically, what we're doing is we're projecting the vertex positions onto the side normal. Okay? So if we go back to our drawing over here, we're projecting these positions onto this side normal, except then we're subtracting an offset, which is this negative side, okay? And really quickly, I did realize we just had an error here. So negative side and positive side, I just sort of drew in the wrong places. These are the negative side of the big box, okay? So this is actually negative side down here, and this is actually positive side up here. So not too much has changed. It's mostly the same, except I just misspoke when I said that this was for the little box. It's actually for the bigger box, okay? So then, continuing on with what we were talking about, though, we're projecting this point here, which ends up right here. Then we're subtracting the negative side, okay? Except, since we're projecting the negative of the normal, it's actually going to end up on the negative side of the axis. So we're going to end up down here. So this is D0. And if we project this up here, we end up right here. And then we subtract offset, and then we're actually going to end up on the opposite side, which is down here. So this is D1. And what do these values represent? Let's look at this visually, okay? So D0 represents this value right here. It represents this distance, the distance this point is penetrating inside this box. And if we look at D1, well, that's representing this distance here. It represents this distance that this is penetrating in the box. So if we color this, since this is the green one, green, this is the D0, and then this is D1, or I may have that backwards. Okay, so look at that. So we basically just got the distances that these are penetrating on this side of the axis, which is -1 and -3. Then let's go back to the code to see what happens. So he says after that, if distance is less than 0, then we add it to our array that's going out, okay? And so basically what he's saying here is if the points are inside the box, add them to the list of the intersecting points. Fortunately for us, they're both actually inside the box. So if we were to write this out, then we could say v out equals, and then this would just be an array with two vertices, which is just 3.93 and 3.91. Okay, so two vertices. I kind of wrote that horribly, but just an array with these two vertices. Okay, what would happen though if, say, we had a larger box, right? So what if actually this sort of went down to here, and the point we had was this point right here, which is 3.90, okay? Or actually that's 3.9 -2. So let's look at this, so if this point was actually 3.9 minus 2, then what we would end up getting is, if we do 0 times 3.9, that's 0, negative 1 times negative 2 is positive 2. So we get a positive 2, which sort of makes sense because that's basically telling us, hey, this point lies outside of our bigger box. So we want to clip it. We want to say, okay, well then clip it to this point right here. And so what does Erin Catto do? Well, he says if distance 0 times distance 1 is less than 0, which basically means if one of them was positive, then what he says to do is find the intersection point of the edge in the plane. We try to walk down the vector by the amount of d0. And if you're still not inside the box, discard the point, otherwise keep the point. So basically what we do is we say, okay, let's try and walk down this side normal vector. So we're going to walk the opposite direction, which is this way, from here. Well, we have to walk down this vector basically however much space we take until we get to where this would be clipped along this edge. And that's not necessarily this length here. If we look at what Erin Catto does, he says interp equals, so interpolated equals distance 0 over distance 0 minus distance 1. So if we look at this, and this is distance 1, and then what he's saying is basically if we do this plus this, we get the whole length, right? This is the whole length. And then if we take out just this portion out of that whole length, then that's sort of the percentage that we have to walk along this vector to get back up to here. And so that is what's happening in this line of code. It's kind of weird, but basically you just walk up the vector until you get back to where you're originally at. And so if that were the case, then we would end up clipping it to the other edge of the other box, which would, or it would end up outside of the box still. So say the box had actually been rotated, so it was something like this. And when we clip it, what we realize is, hey, we're still not actually inside the box. Then we would just discard the point. So that's what would happen in the other case where if distance is greater than 0. Okay, but then we basically just return number out, so how many we got. So we clip those points, which we were able to do successfully. We didn't have to worry about that extraneous point that I mentioned. So we clip the points segments to the lines, and then he does it again, except he does it with the other side, which is the positive side. So if we look at what we just did here, we basically just clipped these points to this side of the box, okay? And then what he does is he says, okay, now clip the points to this side of the box. That way, if there's anything else, maybe the box extended this way, then it would clip it down to here. We don't have to worry about that because we actually have both points inside the box, so we wouldn't worry about that, but that is why he does it again. So then he clips the segments to the line again. And now he says clip points to contains the clipping points. Due to round off, it is possible that clipping removes all points, okay? So then what he does is he just makes sure that we only include points that are actually intersecting. So he does this loop where he loops through 2 points because we should only have 2 contacts at most. He gets the separation from them in the front normal. So basically what he does next is he projects these points onto the front normal. So remember the front's right here, and both of our points, if we projected them onto the front normal, would end up here, leaving us with the separation amount. And if they're behind it, that means that the point is intersecting. If it ended up in front of it, that means this point is not intersecting. So if we look at his code, he does the projection minus the front, and then if that's less than or equal to 0, it means it is actually penetrating the normal's axis. And then he just adds it to our output, adds the normal, adds the position, which we already have calculated, adds the feature, which is basically just the 2 edges, that the instant and the reference edge. And then if need be, he flips it so that it is in a different orientation for whenever he does his extra steps on them. Okay, so hopefully that didn't get too confusing. I tried to walk through the code as best as I could. It's kind of hard to understand, but once you do understand it, you can see how it makes sense. So this is how we will sort of base our solution. If we look at his code as sort of a high-level overview, then what we need to do is we need to first do the separating axis theorem, find the axis of best penetration and the depth. That's sort of this first large block of code. And then second, we just need to clip the points to the other box. Okay, and we can do it the same way he did it, or we can come up with a different way. We'll see how we go about that in the next episode. That is it for this tutorial though. I hope you guys enjoyed it. If you did, please hit like and subscribe. And once again, if this is helping you guys, let me know. It's hard to walk through other people's codes, especially physics code, but it's good to know how this stuff works so that we can continue with our physics engine, okay? In the next episode, we will be implementing this in code. So I'll see you guys then. Thanks.